Hi guys, just write yes in the chat if I'm live. Hi Salesh, just a quick yes in the chat guys if I'm live. Just a quick yes in the chat if I'm live guys, if you can see me, hear me. Yes, I think I'm live. Yes, cool enough. So good evening all of you again for this amazing session of electrostatics. I am Pratik Garg, your master teacher in physics. So till now we have done quite a lot in electrostatics already, as you would be knowing. We have done Coulomb's law, we have done electrostatic field due to ring, point, charge, disk, hollow sphere. We had done Gauss law, we have done flux. So as you would notice that we have done quite a lot. Okay, High Olympiad portal. Okay, so now today we are going to talk about potential. Of course, it's as important as electrostatic field. If you have already studied electrostatic at some point in your life, then you would know that the concept of electrostatic potential would be is very, very important. Okay, so we are going to talk about electrostatic potential, and we are going to talk about the potential of the point charge, potential of the different bodies like ring, disk, hollow shell, sphere. Okay, and so my telegram ID is gpratik880 Olympiad portal. So I hope you would understand. Okay, now so first let's talk about what is actually electrostatic potential. So basically, electrostatic potential at any point, if we talk about what is the value of the electrostatic potential at any point. So electrostatic potential at any point is the amount of work done by the external agent in bringing a unit positive charge. That means a charge of 1 coulomb from infinity to that point. I know it's slightly a complex definition, but listen to me carefully and you would definitely understand. Okay, let us say that at this point the electrostatic potential is Vp. Okay, Vp, or you can simply say you can simply say V as also. Vp means that like I'm saying that let's say this point is P, so electrostatic potential at this point is Vp, right? So I'm saying like that. Okay, so let's say Vp is 10 volts. You know that the unit of the potential is volts. So if let us assume that potential at point P is 10 volts, okay, then that would mean that an external agent would have to do 10 joules of work in bringing a unit positive charge. Then that means in bringing a charge of 1 coulomb from infinity to this point very slowly. So for example, if Olympiad portal brings the charge from infinity to this point very slowly, okay, and the charge is of 1 coulombs, then the potential at this point is 10 volts if the work that that Olympiad portal has done is 10 joules. I'll again speak the statement. So suppose if anyone has to do 10 joules of work in bringing a charge of 1 coulomb from infinity to this point very slowly, then the potential at this point will be 10 volts. So this is the basic idea of the potential, and generally you know that at infinity we assume potential to be 0. Okay, it's a scalar quantity, so best part is that you don't have to face the headache of directions and all, so life will be chilled out, no problem whatsoever. Okay, it's a scalar quantity, no vectors and all. Okay, so many students I have seen that they face problems in directions. Okay, they're not able to visualize directions and all, but this is a scalar quantity, so life is chilled out. Okay, SI units is of course coulombs, joules per coulombs, which is also called as volts. Okay, so you know that joules per coulomb is called as volts. Okay, and we generally assume potential to be 0 at infinity. Now using this definition, let us try to find the potential of a point charge. Okay, so let's try to find the potential of a point charge. Okay, I'll tell you the result beforehand, and then we will see that how to derive that result. Okay, so potential of a point charge, suppose here charge q is kept, okay, and let us say this point is P, which is at a distance of x, okay, which is at a distance of x from q. Okay, so what is the potential of charge q at point P? what is the potential of charge q at point P? So potential of charge q at point P is given by kq by x. I'm sure that many of you would already know this result. Okay, but let me quickly tell you that how to derive this result. Okay, I'll check Olympiad portal, don't worry about that. Okay, and I think I might have missed something, but I'll tell you, I'll have to check. So so basically the potential at point P is given by kq by x, where x is the distance between the charge and the point P. Okay, this is the we can say that the potential at point P. Okay, so I hope you would understand this. Okay, now how to derive this result? How can we derive this? So again, we are going to use the same definition, that work done by external agent in bringing a unit positive charge from infinity to the given point will be equals to the potential of the point at that point. Okay, so imagine that we have kept a charge q here, and we want to calculate the potential at a distance x. So this distance is x, right? So this distance is x. Okay, now, so what is the definition? What's the definition? Definition says that calculate the work done by external agent in bringing a unit positive charge, that means a charge of 1 coulomb, from infinity to this point. Okay, so let us assume that there is one charge of 1 coulomb. Okay, there is a charge of 1 coulomb. Okay, let's call this charge q1, where q1 is equals to 1 coulomb. Okay, let's call this charge as q1, where q1 is 1 coulomb. So let's say this is the charge q1, and q1 is equals to 1 coulomb, right? So now this q1 charge is in another universe, because we have to assume that q1 is at infinity. So you can assume that q1 is in another universe, like, you know, or in different galaxy, like it's very, 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 very far away from q. It's super far away from q. Okay, now someone starts bringing this charge q1 very slowly, and he slowly brings it and deposits this charge at P. Okay, and he brings this charge q1 very, very slowly, and he brings it and deposit it at P. Okay, so what we are going to do, we are going to calculate the work done by the external agent. As simple as that, we are going to calculate the work done by the external agent. Okay, that is what we are going to do. So okay, so basically you can say that work done, what is the formula of work done? How do you calculate work done? So work done by the external agent is given by integration f dot dr. Okay, f dot dr, this is the value of the how you calculate the work done, and this displacement is happening from infinity to x. So this we'll have to calculate from infinity to x. Okay, I hope you understand. Okay, so we can say that what is the magnitude of the force? So basically this will become mod f, okay, mod dr, okay, and the angle between f and dr, so you can see this person is bringing the charge. How is he bringing the charge? Let's say like this, like this. Okay, so this is how he is bringing the charge. Okay, so if you think carefully, so this charge is applying the force in the outward direction. So that means this person is applying the force in the opposite direction. I hope you understand that. Okay, very, very simple. If this charge is applying the force in the outward direction, so this person will be applying the force in the opposite direction, and dr is also in this direction, right? Dr is also in this direction. Okay, so what will you see? Mod f mod dr into cos of 0, because force acts in this direction, and dr is also in this direction. Okay, so what is the value of the force, guys? What is the value of the force? So simply you can see, since this person is bringing the charge very slowly, like, so that means he is applying the equal force as applied by the charge q on this q1, because q is applying electrostatic force given by Coulomb's law. So that means person is also applying the equal amount of force. That's why the q1 charge is moving very, very slowly, right? So so what is the force applied by person? So that is k into q into q1 divided by r square at any instant when the distance between, let's say when the charge has reached this point and this distance has become r. Okay, this distance has become r. Okay, so kq1 by r square, okay, into mod of dr. Now think carefully, dr is a negative quantity. Why? Because as this person will bring the charge closer, r will decrease. So you'll have, when you remove the mod, you'll have to put minus dr. Why? Because you know that if mod is removed and there is a negative quantity inside, then you have to put a minus sign, okay, and cos 0 is 1. So this value you have to integrate from infinity to x, right? So let's calculate this value. So as you can see, minus kq1 will come outside, and this will become minus kq1 will come outside, and dr by r square. What is the integration of dr by r square? So integration of dr by r square is minus 1 by r. So that means you will put one more sign like this, and the integration will go from infinity to x. This is what this integration will look like. Okay, so minus kq1 upon minus r and integrated from infinity to x. This is how this is going to look like. I hope you are clear with this. Okay, now minus sign will be gone. So if you put x in place of r, minus infinity in place of r, so what will this become? So you can see kq1, okay, let me write with another color, or I think it's visible. Okay, kq1, okay, into 1 by x. If you see, if you put x here, so 1 by in place of r, so you will get 1 by x minus 1 by infinity. So this will become 1 by x minus 1 by infinity. So you can see that this will become 0, this term will become 0. This will become kq1 by x. Okay, and remember the value of q1 was 1 coulombs. Okay, so that means since q1 is 1 coulombs, so we will get the value of work done by external agent as kq by x. Okay, kq by x. So if you remember, this is exactly what we had claimed. Work done by external agent in bringing a unit positive charge from infinity to the point P very slowly comes out to be kq by x, and this is in the presence of point charge. This is in the presence of point charge. Hence dear friends, the work done by the external agent, hence the potential of a point charge, at a distance x is given by kq by x. Okay, it is kq by x. Okay, we have assumed potential to be 0 at the infinity, so that means potential of the point charge at distance x is given by kq by x. A very important result you should keep in mind. Okay, so that means potential symbol is V. Potential of a point charge is given by kq by x, as I told you. So if q charge is kept over here, and you have to calculate the potential at point P, and this distance is x, so what will be the potential? It will be kq by x. I hope you have understood. Okay, so very important result, potential of a point charge. Of course, all the other results will be derived from this itself. Okay, all the other results will be derived from this itself, right? So let us do some questions first. So we have to find the net potential at point A. So you can see here what is the situation. Here we have got two charges. Okay, the first charge is 8 coulombs, the second charge is minus 4 coulombs, and this is point A where we have to find the potential. Okay, this is point A where we have to find the potential, and this distance is 3 meters and this distance is 1 meter. Okay, so what we will do, how we will find potential at point A? Very simple. Remember that potential is a scalar quantity, so you don't have to think about the direction and all anything. Simply write the potential due to first charge, which is 8 coulombs, and write the potential due to second charge and add those potential. As simple as that. The way you add two numbers, 7 5 plus 5 is 12, like that. So simply you have to add two numbers, that's it. So if I write, so let's say, so like potential of 8 coulombs, okay, at the location A. So what is this is a point charge. So what is the formula? kq by x, where this distance is 4. But distance between the hi Hema. So distance between the 8 coulombs and A is 4. Hello. So distance is this, so this will be given by k into q. Q is 8 coulombs divided by this distance is, you can see, 4. Okay, this distance is 4 meters. right? So this will be given by 4. So this is the potential of 8 coulombs at point A, right? This is the potential of 8 coulombs at point A. Just give me a sec. Just a sec, guys. Yeah. Hi Rajesh. Actually, I was not able to see the chats, so now I am able to see that. Okay. So potential of 8 coulombs at this point is given by this. Now, what's the potential of this minus 4 coulomb? So if you see that this distance is 1 meter, right? So again, potential of minus 4 coulombs. So V of minus 4 coulomb at the point A is given by KQ by R or KQ by X. So K is this and Q is minus 4. So do not leave out the minus sign. So remember minus sign. K into Q by X. X is how much? 1. So this is 1. Okay. So now we just have to add the total potential. So V total potential at point A. VA means potential at point A. Hello Rajesh, welcome. Okay. Okay. So so what will be net potential? So this will become 8 by 4 is 2. So this will become 2K, right? And this will become minus 4K, right? So total potential is minus 4K plus 2K. So that will be given by minus 2K. Okay. So answer will be minus 2K. Okay. K, you know, value is 9 into 10 to the power 9. So answer will be, if you want to put the value of K, you can put it 9 into 10 to the power 9. So this will become minus 18 into 10 to the power 9 volts. The SI unit of volt potential is volts. Okay. Olympiad portal, bro, I don't get angry. I like hardly get angry. How can you say that, brother? Okay. So I hope you have understood this. Okay. So let's move to the next question. Okay. Let's move to the next question. So here, if you see, you have to find the value of charge Q such that potential at A becomes 0. Let's understand the question. There are 3 charges. This is 3 coulombs. This is Q and this is 3 coulombs. So there are 3 charges, 1, 2 and 3. Okay. And you have to find the value of Q such that potential at point A becomes 0. The distance between 3 coulombs and A is 5 meters and this distance is also 5 meters, whereas this distance is 4 meters, right? So we can say that net potential at A should be 0. Again, the idea should be very, very simple. Just write the potential due to all the charges. Just write the potential due to all the charges at A and add up to 0. Okay. So let's do this question. So what is the potential at A? What is the potential at A? What is the potential at A due to first charge, which is 3 coulombs? What is the potential at A due to this charge? So it is simply KQ by R. R is 5 meters. So it will be K into Q. What is Q? Q is 3 by R is 5 meters, right? So KQ by 5. Okay. Plus what is the potential at A due to the second charge? So KQ by 4. Okay. So plus K into Q by 4. Okay. And what is the potential at A due to the third charge, which is 3 coulombs? So again K into 3 by 5. K into 3 by 5. Okay. So net potential should be 0. Net, you should equate it to 0. This is what you should do ideally. Simple life, no problem, no tension. Okay. So you can say that K is going to get cancelled. So whatever is getting cancelled, cancel it. Okay. Do not be burdened. So K gone. So 3 by 5 plus 3 by 5, 6 by 5. Okay. So what do you get from here? Q by 4 is equals to 6 by 5 will come on the RHS. It will become minus 6 by 5. So 6 4 ja 24 by 5. Okay. That means Q comes out to be minus 24 by 5. Okay. So which you can write as minus 4.8 coulombs. Minus 4.8 coulombs. So that means if the charge Q becomes minus 4.8 coulombs, potential at A will be 0. Yes, Rutvika, you are correct. Okay. So I hope you got this. Let's move to the next question. Okay. So see this question. This is slightly a good question. See carefully what we have to find. 12 equally spaced charges, each of value Q. Okay. 12 equally spaced charges, equally spaced, each of value Q, are placed along the circumference of the equatorial plane. I'll explain this question. Don't worry. find the potential at the top point. The radius of the sphere is r. Okay, so imagine what is happening. Imagine a sphere. Okay, imagine a sphere. Okay, so like assume that this is earth. Okay, so you know that this will be the equator, this will be the equator. Okay, and this will be the north pole, right? So this is the equator, right, and this is the north pole. So along the equator, okay, along the equator you have placed 12 equal charges at equal distance. So 1 2 3 4 5 6 7 8 9 10 11 12, like that. So along the equator you have placed 12 equal charges, each of value q, let us say. Okay, each of value q, and like each of them are equally spaced. Okay, and you have to find the potential at the north pole, that means the top point of the earth. So that means you have to find the potential over there. Okay, now very easy if you think carefully. Okay, let's say what is the, so let's say this charge is q, so that means each of them is q, each of the charge is q, and this is the center of the earth. Okay, this c is the center of the earth. Okay, now you know that this is radius. Okay, and this is also radius. Okay, so this is radius, this is also radius, so r and r. That means if you say that this is north pole, n, so what is this distance, guys? What is this distance? Distance between this charge and north pole. Can you think carefully? So r is this and r is this, so that means this distance will be root 2r, right? Root 2r, this distance will be root 2r. Simple Pythagoras theorem. Okay, simple Pythagoras theorem. Okay, so can you tell me the potential of this charge at north pole? Yes, cool and casual, very easy. So kq by root 2r. Okay, kq by root 2r will be the potential of this charge. So k into q by root 2r is the potential of this charge, that means single charge at north pole. Cool. So potential of this charge, single charge at north pole, is kq by root 2r, as simple as that. Okay, now if you think carefully, that same will be the potential of all other charges as well. That means, for example, if you talk about this charge, so this is also at a distance of root 2r. Think carefully, this is also root 2r, this is also q. Okay, if you think in 3 dimensions, then this is also at a distance of root 2r. If you think in 3 dimensions, hi Prithvi, hello. So if you think in 3 dimensions, this is a sphere, so each charge is at a distance of root 2r. Okay, so like for example, if you imagine this charge, which is right, like on your side, so its distance from center is r, and this distance also r. So can you see that this distance, which is Pythagoras, will also become root 2r. So again, if you think carefully, all the charges are at the same distance from the north pole. So that means each charge will create the same potential of this value, kq by root 2r. Hence the total potential at n. Okay, this is the potential of q at n, this is the potential of q at n. So total potential, V total at n, will be 12 into vq, 12 into vq. So that means 12 by root 2 will be 6 root 2 kq by r. I hope you have got it. Yes, Rutvika, you are correct. So 6 root 2 into kq by r, that will be the answer for this question. So this will be the potential at the top point due to the all the charges, right? Now let's find the potential of a ring, which this is the formula you have to remember, this you have to recollect, yeah, keep in mind. So that means assume that this is a ring. Okay, assume that this is a ring, this is the center of the ring, and this is the axis of the ring. Okay, this is the axis of the ring. Okay, and this ring contains the charge q, spread along it. Okay, okay, now let's say we have to find the potential, let's say at this point P, and distance cp, that means center and p is x. So this distance is x, and the ring is of radius r, ring radius is r, okay. So I hope now you have to find the potential, at point P. Okay, you have to find the potential at point P. It's G Pratik 880 Olympiad portal, not 830, it's 880. Okay, so now, so how can you find the potential at point P, very simple, you have to as you have to split this ring in small particles. So assume one such particle is like this. This is one such particle. Okay, assume one such particle which is having charge dq. Okay, total charge on the ring was q, and dq is the charge which is just present on the small part of the ring. Okay, dq is what? dq is a very small charge present on this much part of the ring, like very tiny part of the ring. Okay, like this much. Okay, so what can you tell me the potential of? Can you tell me the potential of this dq at point P? So can you first think that this dq is behaving like a point charge? Yo, no. Write yo in the chat if you feel it is correct. Yo, no. So if you think that this is acting as a small point charge, okay, then we can apply the formula for point charge. Yes, we can apply the formula for point charge. Okay, so for this small charge, this small which is acting as a point charge, the point P is at a distance of how much? So this is r and this is x. So this distance is nothing but under root of r square plus x square, right? So how much potential will this point, will this small charge dq create at point P? So very small. So we can write dv is equals to, why are we writing dv? Because the charge is very small, so it will create a very small potential. Hi Harmit. So that means it will create a very small potential. So what will be the potential at point P? So formula is kq by x for a point charge. The formula is kq by x. So we can say that it is k dq by this distance under root of r square plus x square, under root of r square plus x square. This is the potential. Okay, due to the small charge dq, due to the small charge dq. I hope you got this. Okay, now for the whole ring, you will have to integrate. You or no? Cool. So for the whole ring you'll have to integrate. Okay, so just integrate this for the whole ring. Okay, so from 0 to v. Okay, and if you think carefully here, what is the this is the integration of q. Okay, because r is constant, x is also constant, x is not changing for each element. Like if you take this element, this element, this element, whether this element, if you think carefully in 3 dimensions, the distance between each element and the point P is not changing. This is also under root of r square plus x square. This is also under root of r square plus x square. If you think in 3 dimensions, so this is ring. Okay, this is ring and this is the axis. So each element will have a distance of under root of r square plus x square. If you think carefully. So I hope you are understanding this. So that means this thing will come out. So this will be integrated from 0 to q. So this thing will become v is equals to k upon under root of r square plus x square will come out, right? And this will become integration of dq 0 to q. So this, of course, you can see very easily, dq will become q after integration. So this becomes kq by under root of r square plus x square. Okay, so this is the potential of a ring at a distance x from the center on its axis. Kq by under root of r square plus x square. This is the potential of the ring at a distance x from the center. The great thing about this formula is that it is valid even for a non-uniformly charged ring. You should be able to understand why is it so. It's because even if the charge is non-uniformly valid, even if you just place all the charge at a single point, the idea is that the distance between any point on the ring and the point P is not changing. So even if the charge was just located at this much part, okay, so then also you would have done the same thing. You think carefully, then also I would have made the same type of integration, because the distance between any point and the P is not changing. So this is the formula valid even for a non-uniformly charged ring. The great part of this formula is that. By the way, what is the formula? Kq upon under root of r square plus x square. See this formula very carefully, because I will use this formula in deriving the potential of a disk. Okay, so what is Q here? Q is the total charge on the ring. Remember, what is capital Q here? Capital Q represents the total charge on the ring. R is the radius of the ring, x is the distance between the center and the point P. X is the distance between the center and the point P. So this is the formula. I hope you are with me till here. A very, very simple formula, nothing to worry. Okay, very, very easy formula. Great, Rutvika has understood. So let's move on to the potential due to the disk. Okay, I hope you have got until here. So let's understand the potential due to the disk. Okay. So potential of a disk. Okay, so now you know that disk is a uniformly charged body. Disk is a uniformly charged body, and the charge is spread on the area. That means the charge is whole spread on the area, and let us say sigma is the charge density. So what is sigma? Sigma is the charge density, and r is the radius of the disk. R is the radius of the disk. So remember here, capital R I am saying is the radius of the disk. Okay, and sigma is the charge density. So what do you understand by sigma? Total charge upon total area. What is sigma? Sigma is the total charge upon total area. That means capital Q charge, if you have spread capital Q charge on the disk, then sigma will be given by Q upon pi r square. Okay, so that means sigma is nothing but Q upon pi r square. This is what sigma is. Okay, we will represent our answer in terms of sigma only, remember, because for the case of the disk you just have to memorize the result in terms of sigma only, right? So what we have to find? We have to find the potential of this disk at the point P, which is located at a distance x. So this distance is x. Okay, so this is what you have to find. Okay, and C is the center of the disk. C is the center of the disk. Okay, so how should you go about this? Can you write in the chat box? How should you go about this? Okay, so if you think carefully, we should break, we have done this many times. We should break this disk in small rings, right? We should break this disk in small rings, correct? And we should write the potential of the ring using the formula that we had just derived, right? Remember, this was the formula that we had just derived, kq by under root of r square plus x square. This was the formula of the ring. So we should write the potential of the we should break this disk into small elements, and we should write the potential of each of the ring and then add it up to get the potential of a disk. Okay, so if you think carefully, what I am going to do, I am going to represent one such ring. Okay, so see carefully, this is one such ring. Okay, this is one such ring. Okay, so I was able to draw a nice diagram, I guess. I don't know if it's nice or not. Let me draw this outer wala ring slightly better. So what do you think? Is it an okay diagram? Like, are you able to analyze what I'm saying? So this, I think, looks okay, right? So this type of ring, okay, this is of radius small r. Okay, let's say this is of radius small r. Okay, and thickness is dr. So if you think carefully, guys, okay, this ring is of radius small r and thickness dr. Let me draw this ring again over here. Let me draw this ring slightly in a better way, so you can see over here that this is the ring I was talking about. Okay, so this ring is of radius r. Okay, this ring is of radius r and thickness is dr. So this is the ring I am talking about, right? Now, first thing, can you tell me what is the area of this ring? That means I am talking about this area. Right? So many times you would have noticed that how to write area of this type of ring. So simple, circumference multiplied by thickness. That means 2 pi r is the circumference multiplied by this small thickness dr. Okay, so the area of this ring will be 2 pi r dr. Okay, yes, Rutvika, correct, absolutely correct. So area of this ring is 2 pi r dr. Nice, you are doing great. So 2 pi r dr is the area of this ring. So how to write the charge on this ring? Very simple. What is charge density? Charge density is charge upon area. So charge will be given by density into area. right? What is charge density? What is sigma? Sigma is the charge per unit area, that means charge upon area. So how you write the charge on this ring? Charge into area, sigma d, absolutely correct. So that means dq is the charge on this ring, absolutely brilliant answer. So that means dq will be given by sigma into dA, right? So sigma we will keep it as it is because we have to represent our answer in terms of sigma only. We have to learn the answer in terms of sigma only, and dA value given by 2 pi r dr. Okay, so this is the value of the charge. Okay, now what was the formula of the potential of a ring which we had just derived? So if you go back, k into charge on the ring divided by under root of r square plus x square, where r was the radius of the ring. Be careful here. Here capital R represents the radius of the ring. Okay, so what is the radius of this ring? Radius of this ring is small r. Radius of this ring is small r, and the charge on this ring is dq. So what will be the potential of this ring, which is drawn here as well? Potential of this ring at point P. So you can say that dV will be is equals to k into dq. K into charge on the ring divided by under root of radius, radius square plus x square. So what is the radius of this ring? R square. Okay, R square plus x square, right? This is the potential. Okay, so Mahalakshmi, I couldn't understand what you're saying. Which between come rank in JEE? I'm not able to understand what you are saying. So could you please elaborate? So dV is k dq upon under root of r square plus x square. This is the potential of this ring, or you can say this ring at point P. Okay, now disk is made up of many such rings. So if you want to find the potential of a disk, what you got to do? Pretty simple. Just add the potential of all the rings. Okay, so just add the potential of all the rings. So we can integrate. Okay, so here what is the variable? Put the value of dq here. Okay, so let me put the value of dq first. Let us put the value of dq first. Right, so here if you put the value of dq, what will it become? K into sigma into 2 pi r, okay, into dr divided by under root of r square plus x square. Now we can integrate this expression. JEE rank selection, Mahalakshmi, if you get anything under 20,000, you will qualify, but for a good college and good IIT and good branch, you should ideally get a rank within 7,000. So in that case you will get a decent IIT and a decent branch. So now you can integrate this. So basically what we will do, we will integrate this. Okay, so basically dV, let me write here. So what is dV? dV comes out to be k sigma 2 pi will come outside, they are all constants. Okay, so k sigma 2 pi, they will come outside. Okay, and inside the integration, what will you have? R dr upon under root of r square plus x square. So R dr upon under root of r square plus x square, and r will go from 0 to capital R. Okay, and potential will go from 0 to V. I hope you have understood till here. Okay, so if you see carefully, LHS will become V. K, how do you write K? So K is 1 upon 4 pi epsilon naught. Okay, so you can see that this will become sigma upon 2 epsilon naught, because K is 1 upon 4 pi epsilon naught. Okay, if you want, I can write that fully as well. So K is 1 upon 4 pi epsilon naught into sigma into 2 pi. So that means sigma into 2 pi, right? And now we have to integrate this. So this type of integration we have done so many times. Yes. So how do you integrate this type of expression? R square plus x square you can put any variable L square. Let us say we put R square plus x square as L square. Okay, so we are saying R square plus x square ko I am saying is L square. So if you differentiate this, remember x is constant, variable is r, this integration is of r. So if you differentiate this, you will get 2r dr. X is constant, so it will become 0. So it will become 2L dl, right? So r dr is nothing but L dl. Cool. So what will this become? So if you, this was the integration of r, now you have changed the integration to L, so you will have to change the limit as well. Okay, so you have to change the limit as well. Please ask Mahalakshmi, I'll tell you what is the doubt. So if you put small r as 0, so L will become x. Okay, and if you put small r as capital R, so you will get under root of r square plus x square, and here you will get L dl upon under root of r square plus x square is under root of L square, right? So you can see that this, then this will be cancelled. Okay, here this 2 pi and this will become 2, so this will become sigma upon 2 epsilon naught, right? And here you can see that this whole thing has cancelled, so only dl will be left. So dl when integrated will become L, and the limits is x say under root of r square plus x square. So finally we have gotten our answer. Dx, there is no dx Mahalakshmi here. Here we have got dr. Okay, x is constant. Okay, there is nothing called dx over here. Here x is present, which is a constant. X was the distance between the center of the disk and the point P, which is not changing. Okay, here r was the radius of the ring, which was changing. So r is a variable, small r. Okay, so that means what do we get from here? Sigma upon 2 epsilon naught. And if you put under root of r square plus x square is in place of L, so you will get under root of r square plus x square minus, if you put x instead of L, so you will get this. So this is the formula which you should remember. This formula is useful for like deriving the, this formula is useful for writing the potential of a disk. Under root of r square plus x square minus x. Okay, this class is valid both for mains as well as advanced, Chandana. Okay, this formula is useful for mains as well as advanced. In fact, last year also there was a question from the potential of a disk in which this formula was being used. So in JEE advanced, of course. So JEE advanced as well as JEE mains. Okay, in fact boards also. So sigma upon 2 epsilon naught into under root of r square plus x square minus x. This is the potential of a disk, a very important formula. You should remember that here r is the radius of the disk. Okay, here capital R is the radius of the disk. Remember this. Capital R is the radius of the disk. X is the radius of the, x is the distance between the center and the point P on the axis. Okay, point P on the axis. Okay, so this is the result. I hope you guys are cool and casual, have understood this till here. Cool enough? Okay. Now should we move to the potential of a hollow shell, which is also a very important formula. Potential of a hollow shell, very useful formula. Okay, potential of a hollow shell. Okay, so let's see how to write the electric potential of a hollow shell. Okay, so then let's say this is the hollow shell. This is the hollow shell which is of radius r. Okay, which is of radius r, and the total charge q. Total charge q is uniformly distributed on the shell. Total charge q is uniformly distributed on the shell. So now I am going to tell you the formula only. Derivation, I guess you guys can do. The idea will be again integration and all those things. Okay, so let's just see the formula. Formula is very important. Okay, so the total charge q is thank you, Chandana. So total charge q is distributed uniformly. Total charge q is distributed uniformly on the shell. Remember, q is distributed uniformly on the shell. Okay, q is distributed uniformly on the shell. Okay, so what is the value of the potential? Now here there are two cases. One can select point P inside the shell. Okay, so this region, if you see, this region is inside the shell, whereas this region is outside the shell. Okay, so what happens if you select the point inside the shell? The formula is different. And what happens if you select the point outside the shell? Formula is different, remember. Okay, so let us say C is the center of the shell. Let us say C is the center of the shell. Okay, so if you select point P inside the shell, let us say we select point P over here such that this distance is x, No, Mahalakshmi, answer is not 0. Electric field is 0, but potential is not 0. Electric field of course is 0, but potential is not 0. We are talking about the potential. Potential is constant here. Okay, so we can say that potential is kq by capital R. Okay, if x is less than equals to R. So that means as long as x is less than radius, think carefully, as long as x is less than radius, so point P will be inside. Okay, because this is radius and this is x. So if x is less than radius, so point P will be inside. But if x is greater than radius, if this distance is more than radius, so point P will go outside, then you cannot use this formula. What does this formula tell you? This formula tells you that at any point inside the shell, the potential will be constant, because K is constant, Q is constant, capital R is also constant. What is capital R? Capital R is the radius of the shell. So this is a very good result which you should remember, that potential at any point inside the shell is always constant. It is given by kq by capital R, where q is the radius, q is the charge on the shell, and remember it's a uniform distributed charge. Okay, and what is the potential if the charge q lies outside, if the point P lies outside? So suppose we choose a point P outside like this. Okay, suppose if this is point P, okay, and so in this case x will be more than radius. You can see this is x, so you can see x has become larger than radius. So if you can see that x is larger than radius, okay, so what will be the potential? So in this case the result is kq by x. That means whatever is the distance between the center and the point, kq by x, right? So this is the result. Look at this result very, very carefully. Yes, radius of the sphere is capital R. Okay, radius of, no, this is inside outside both is R only, Mahalakshmi, because this is not a thick shell, this is a thin shell, so radius of the shell is R. Okay, so outside, just Rutvika, you are right, absolutely correct answer. We have taken the symbol as x instead of R. So if you are taking symbol as small r, then you can say that kq by r, but I have taken the symbol as x. So the answer will be kq by x. What is x? X is the distance between C and P. X is the distance between C and P. So this is the value of the potential at point P. This is the value of the potential at point P, kq by x. I hope you have understood clear, right? So potential at point P, if it lies outside, the result is given by kq by small x. Potential at point P, if it lies inside the shell, it is given by kq by capital R. This is the idea. I hope you have gotten till here. Okay, make sense, guys? Okay, so this is a very, very important result. Please do keep this in mind. Okay, now we are going to talk about one dirty formula. So what is dirty formula? Actually, we are going to talk about the potential of a solid sphere. So the formula is slightly dirty, but it is very, very important. Okay, why am I saying dirty? Because the expression is very, very dirty. You have to remember that it's a big expression. So that is why it's slightly dirty, but you have to remember that. The important point is that you have to remember that it's slightly troublesome to remember, but again, very important, and that will be used in gravitation as well. Okay, so let's see the potential of a solid sphere. Okay, so how do you remember the so what is the potential of a solid sphere? Let us see. So first of all, let's say this is the solid sphere. Okay, and it is a solid sphere. The total charge is q, which is uniformly distributed across the volume. What is the difference between the solid and the hollow sphere? In the hollow sphere, the charge is distributed on the surface, whereas in the solid sphere, the charge is distributed throughout the volume. Okay, Mahalakshmi asks, if x is less than r, what happens on outer surface, sir? If x is less than r, then how can you reach the outer surface, Mahalakshmi? If x is less than r, that means you are lying within the shell, right? That means if point, like, what is x? See carefully, this is x. So if x is less than r, that means point P is inside the shell. It cannot go outside. For going outside, x has to be greater than r. Okay, so this is what we are saying. If point P is inside the shell, so x is less than r. in that case. So for that case you have to use this formula, kq by capital R. Okay, but if x is greater than R, that means point P is like CP distance has become greater than R, capital R. So in that case you have to use this formula, kq by x. This is what we are saying. Okay, yes. So coming back to the solid sphere, what is the formula? Again here there are two cases. R is the radius of the sphere. R is the radius of the sphere. Okay. Rutvika, charge always spreads on the surface for a metallic sphere, not for a non-metallic sphere. You're correct, but that is true only for a metallic sphere or a conducting sphere, okay, which you call a conductor. So that charge will be on the if it's a conducting sphere, then charge will spread on the surface. If it's a non-conducting sphere, then charge will not spread on the surface. So when we say a solid sphere, then we inherently assume that it's a non-conducting sphere. So that means when we are specifically saying that charge was spread throughout the volume, then inherently we assume that this was a non-conducting sphere. So for a non-conducting sphere, charge will not spread on the surface. It will stay like wherever it was given. It's like an insulator. Okay, I hope you got your doubt cleared. Okay, so again for this radius R, like this is a solid sphere, non-conducting solid sphere of radius R. Okay, and the charge is uniform distributed throughout the volume. Okay, now again here we have to choose two cases. Okay, what happens if the point lies outside and what happens if the point lies inside? So let us say C is the center of the sphere. Okay, now again, so if the point is outside, so again the formula remains the same. So for example, if CP distance is greater than R, so you can see if x is greater than R, so if x is greater than R, so if x is greater than radius, so P will lie outside, just like the previous case. If x is greater than R, then P will lie outside. Okay, so in that case formula will be kq by x. Remember, this is the same formula that we got for the shell. So kq by x, this is the same formula that we got for the shell, will also be valid for the solid sphere. Okay, but if the point lies inside, that is when formula becomes dirty, but it's important formula. Okay, so if the point lies inside, suppose this point P is lying inside. Okay, so we are calling this as x. Okay, so if point P lies inside, so x is less than or equals to R. So in that case, what is the formula? Does anyone of you know what is the formula? So in that case, the formula is kq by 2r cube into 3r square minus x square. So this is the formula. Okay, kq by 2r cube into 3r square minus x square. So you can remember that this is, so you can understand that this is slightly dirty in nature. That is why I was calling this as dirty formula. Okay, but quite important. Okay, so kq by 2r cube into 3r square minus x square. This will be the formula. Okay, this is the result at the when the point lies inside. So kq by q is the total charge on the sphere. R, you know, is the radius of the sphere, and x is the distance from the center. Okay, and you have to use this formula when x is less than R. If x is greater than R, then in that case use above formula kq by x. I hope guys you have understood till here. Okay, for example, if someone asks that what is the potential at the center. Okay, suppose we have to find the potential at the center. Okay, example. Okay, so potential at the center. So for center, what you can say? X will be 0. For the center, you can say that x will be 0. Yes or no? Right? Because point P is at the center, so x is 0. So if you put x is 0 here, so what will this become? Kq into 3r square divided by 2r cube. That means this becomes 3kq by 2r. This is the potential of a solid sphere at its center. I hope you have understood. Cool enough? So guys, I hope you have understood till here. We have done the potential. We have done the potential of a point charge. We have done the potential of a disk, of a ring, of a solid sphere, of a hollow sphere. Right? So we'll stop here. That's all for today. We'll continue from here in the next session. I hope you have enjoyed today's session. See you all. Bye bye. Love you. Good night.